Hello and welcome to Take 5 with Automation World. I'm David Miller, Senior Technical Writer for Automation World. The topic of today's video is going to be something called Raman Spectroscopy. Now, what is Raman Spectroscopy? So it's not related to the popular noodle dish that many of us may have eaten in college. Rather, it takes its name from C.V. Raman, who is the physicist that pioneered it. And what it is, more specifically, is simply a non-invasive technique for determining the chemical composition of material samples by exposing them to electromagnetic radiation. Now, I'm not a physicist, nor am I a chemist, but I can give our viewers a high-level overview of how this works. In essence, what occurs when Raman spectroscopy is used is that photons, or electromagnetic radiation, basically we're just talking about light of some sort, light beams, is fired at a substance. And then depending on the molecular makeup of that substance and the way its molecules are vibrating, the light that is reflected back will undergo certain minute variations in its wavelength, which a Raman spectrometer can detect and analyze. So from there, the device can make assessments of all kinds of variables, such as, for example, the common ones we see in the process industry's temperature, level, flow, and pressure. So it's a very neat toy, right? But the important thing to ask is, why is it relevant to industry? Well, in a word, it has several advantages over other methods when used either to monitor process variables for control sorts of purposes, inline in process industry applications, or for quality control procedures in process industries such as chemical or pharmaceutical production, where an output product needs to be tested and verified for regulatory purposes or something of this nature. So what are the advantages of using Raman spectroscopy for monitoring process variables and conducting quality control tests in process industry environments? So there are a few. First of all, when you use conventional field instruments to gather measurements and analysis parameters such as the previously mentioned level, flow, pressure, temperature, and so on, these variables are recorded individually and then fed into a regression model, which is basically just a statistical tool for measuring the relationship between multiple variables. And if you've ever seen an infographic, a graph, you've seen this before. It allows you to see how those parameters are changing over time in the form of a visual slope or curve. We've all seen this before. So the issue, though, is that when you do this, you have two drains on you, both of which Raman spectroscopy can eliminate. So the first is that you have to use many different sensors to ascertain each different parameter. And the second is that you would have to program a new regression model for each new application you're looking to measure. So basically what you have is a situation where it's very asset intensive, lots of sensors, all of which need to be purchased, installed, so on and so forth, and then time intensive in terms of the need for repeated reconfigurations. By contrast, with Raman spectroscopy, the promise at least is that you can measure multiple variables simultaneously and have results delivered in real time so that you don't have to run a process, check the data, reconfigure, and run again, but instead can engage in an on-the-fly kind of optimization. The idea being that this would help you speed cycle times, increase yields. If there's a problem with a batch or something like that, you can figure it out before the batch is finished and correct it, things like that. So for inline usage, this is relatively new technology. Currently, industrial applications for Raman spectroscopy are mostly limited to a laboratory context. And so basically, when set up in a lab, instead of integrated directly into a process control system, you have to draw the samples and then transport them to the lab where you run the spectrometer on it. And what this means is that they can change during transport. And then, of course, there's the issue of delay in obtaining the result, like I said, meaning that you can't engage in a corrective measure while the process is still running. You only know after it's finished that there's a problem at all. So this would lead, obviously, to various types of wastage. But again, this is something that is developing. We are beginning to see Raman process analyzers for inline applications hit the market. So if you're interested in reading more about that, if you'd like to learn about these products, feel free to click the link below this video.